Hello. So my project title is Implementation of a 16-bit Mini RISC Processor using TFT LCD display on Xilinx RTX 7 Edge board. So we all know how does a RTX 7 Edge board look like. This is how my LCD display looks like. To connect both of these components, I am using this pin layout diagram. So what is RISC? RISC stand for Reduced Instruction Set Computer. The main idea is simple. Instead of having hundreds of complex instructions, we use a small set of simple instructions, each of which runs in exactly one clock cycle. This makes the hardware simpler, faster, and easier to pipeline. Every instruction in my project is 16-bit. All arithmetic works on register R0 to R5, not memory directly. Each instruction complete in exactly one 50 MHz clock cycle. Only 6 opcodes needed for full demonstration. If I talk about the overall architecture, the CPU is built as a single cycle processor. This means every instruction fetch, decode, execute, write back happen within one clock cycle. The 50 MHz clock cycle gives us 50 million instructions per second. Let me walk you through each module. The program counter is the simplest module. It just stores an 8-bit address and updates it on every rising clock edge. On reset, it goes back to address 0. The next program counter input is computed outside and either incremented by 1 or jumps to a branch target. The instruction memory is essentially a lookup table. The program counter value is the address and the output is 16-bit instruction at that address. We have 6 real instructions followed by a BEQ, which is branch if equal, which is nothing but halt. Once all operations are done, the CPU loops on a instruction 6 forever without corrupting any register. The control unit is a pure combinational block, no register, just a case statement. It looks at the top 4 bits of the instruction, the opcode, and set signal like reg underscore wire, which allow writing the register file. ALU SRC, which select between a register or immediate value for the second ALU input, and branch, which enables the BEQ jump. The register file has 16 registers. 2 are read combinationally, meaning they are available instantly as soon as the address changes. 1 write happen on the rising clock edge. We also have dedicated read ports for R1 and R2 that go directly to the display controller so we can always show the values. The ALU is another purely combinational block. It takes 2 register inputs and an operation code, instantly produces a 16-bit result. For add and sub, these are standard arithmetic. For AND and OR, these are bitwise operation, meaning each bit of the result computed independently from the corresponding bits of the 2 input. Now coming to SPI master. What is SPI master? Stands for Serial Peripheral Interface. It's one of the most common protocol for connecting microcontrollers and FPGAs to peripheral devices like display, sensor, and memory chips. Our FPGA is the master, it generates the clock and sends data. The LCD is the slave, it just listens. The SPI master divides the 50 MHz system clock by 16 to get 3.125 MHz. For each bit, it first divides the MOSI line, the most significant bit of the shift register, then pulse the clock line. The LCD reads MOSI on the rising clock edge. After 8 bits, the master asserts the ready signal to tell the display controller that the byte has been sent and the next byte can be loaded. The LCD display is a 1.8-inch color display that communicates with the FPGA over SPI, meaning all the data is sent serially along with data on the MOSI line, synchronized to the SPI clock. Before it can display anything, the LCD requires a mandatory initialization sequence. Hardware reset via the RST pin, followed by a software command like SLP out to wake it up from sleep, COL MOD to reset RGB colors format, and DISPOM to turn it on. The entire screen is then cleared by writing 40960 bytes. The display controller is implemented as a dynamic state machine which states reset, initialization, draw, ideal, clear, and again draw. Every time the button is pressed, the FSM clears the screen first to prevent text overlap, then redraw. Drawing text usually uses a 5x7 pixel bitmap font. For each pixel, the controller sends 13 SPI by KSEN to set the column, RAST to set the row, and RAMWR with the 2-byte RGB colors. The DC pin distinguishes command from data. The screen displays 5 rows, operation number in yellow, instruction unit in cyan color, a register values in white, and the result in gray, all driven in real time from the CPU register output. Let's see the demonstration part.
So this is the instruction file for now. As you can see, the first instruction is add I, which is nothing but add immediate. What it does, it store a value, hex value in the register. The other instruction is add ADD. What it does, it takes two register and store the value in another register. The third instruction is SUB sub. It also take two register and do subtraction of those two. And an or are two bitwise operator, like they will do bitwise operation. I have written the constraint file according to the pin diagram I showed earlier. I have connected my FPGA board with the LCD display with jumper wires. You can see that it is running the first operation OP1, in which add immediate R1 is equal to 5. That means we are putting R1 as value 5. To go to the next instruction, I have to click a button. I have to click this button to go to the next instruction. If I press now, we will go to the next instruction. Okay, now we can see we are in operation 2. Add immediate again, R2 is equal to 3. Now if I press again, now we can see the operation 3, which is add, in which I already told you we are taking two register R1 and R2. We already took the value in operation 1 and 2. Now when we are adding, we can see in R3 that we got the value 8. Now going to the another operation 4, which is subtraction. Again we can see in the R4 that we got the value 2, which is 5 minus 3. Coming to end, we got R1 and R2. We will get R5 as 1. Similarly, if we do operation 6, which is OR, we will get 7. If I press again, as there are only 6 operations, it will go back to the first operation.
Some possible future extension can be adding more instructions like MUL multiplication, NOT, and XOR. Furthermore, we can add functions like SHL shift left, and other instruction can be shift right SHR. Thank you.